Welcome to MRL. In this learning session, we'll be learning about number system. Now, what is a number system? The number system comprises of natural numbers, whole numbers, integers, rational numbers, irrational numbers, and real numbers. I have separate learning sessions on all of these numbers. You can please go through them to understand the concepts which you are going to discuss in this learning session clearly. Now, when we talk about real numbers, it is a set of rational numbers and irrational numbers. Rather, it's a union of a set of rational numbers and irrational numbers, and it is denoted by capital R. Now, the real numbers set can be represented by a Venn diagram. This is a Venn diagram of real numbers. It is the union of rational numbers and irrational numbers. Both rational numbers and irrational numbers sets are infinite sets, and irrational number set is in fact a bigger, larger set as compared to rational numbers. Both are infinite sets. So please remember that. So this is a Venn diagram. Now, for understanding the concept what we are going to discuss in this learning session, I suggest you please go through the learning sessions on natural numbers, whole numbers, integers, rational numbers, irrational numbers, and real numbers. Their properties and operations are which are recorded as separate learning sessions and are presented to you for your understanding, so that the concepts which we are going to discuss in this learning session become much easier. Now, there are different types of decimal expansions. As you know, the different types of decimal expansions are terminating decimal expansions, non-terminating recurring decimal expansions, and which can be pure or impure, and also non-terminating non-recurring decimal expansions. So please remember that. Now, the decimal expansions represent different types of numbers. Now, the decimal expansions which represent rational numbers are either terminating or non-terminating repeating, and in that non-terminating repeating we have got pure recurring and mixed recurring. This is already discussed in rational numbers learning session, which is a separately recorded learning section. Please go through it. Now, coming to the decimals representing irrational numbers, they are non-terminating and non-repeating. Again, this is also recorded as a separate learning session. You may please go through it. Now, in this session, we will be learning as to how to find the types of decimal expansions of Q. Now, if you have a rational number p by q, we can divide p by q and get a decimal expansion. We can find out what type of decimal expansion it is. Is it a terminating decimal expansion or a non-terminating recurring decimal expansion, pure or mixed? But if you, without dividing p by q, how to find the type of decimal expansion of rational numbers is what is our study. And for that, the method is very simple. First of all, convert this p by q so that p and q are co-primes. P and q should be co-primes. If p and q are co-primes, then q has a term, then p by q has a terminating decimal expansion if prime factors of q has only powers of 2, powers of 5, or powers of 2 and powers of 5. Now, what does this mean to us? Let us take an example. 875 divided by 1000 is a rational number. Now, we do not know whether it is terminating or non-terminating recurring decimal expansion. Now, to know this, first of all, find the prime factors of 875 and 1000. It is 7 into 5 raised to 3, 2 raised to 4 into 5 raised to 4. So now we know that 5 raised to 3 can be cancelled with 5 raised to 4. We get only 5 here. So we have the numerator as 7, that is p is 7, and q is 2 raised to 4 into 5. The q is a product of powers of 2 and powers of 5, and therefore this will have a terminating decimal expansion. So please remember that. So therefore the denominator of q is a product of powers of 2 and 5. Therefore the given rational number has terminating decimal expansion, because the terminating decimal expansion condition is that the prime factors of q have to be what you call powers of 2, powers of 5, or product of powers of 2 and 5. Now, if p by q is a rational number, where P and Q are co-primes. If P by Q has a non-terminating recurring decimal expansion, if prime factors of Q are not powers of 2 or powers of 5 or product of powers of 2 and powers 5. That means, let us understand this with an example. 7 by 9 is equal to 7 by 3 square. Now here Q is not powers of 2, that means it is 3 square, which is neither 2 raised to m or 5 raised to n or 2 raised to m into 5 raised to n, and therefore 7 by 9 has a decimal expansion which is non-terminating and recurring decimal expansion. So that is how we identify the type of decimal expansion which a rational number can have. Now the next and very important discussion is to prove a given number is irrational. Now for example, root 2 is irrational. Root 2 is irrational. Now to show that root 2 is irrational, what is the procedure? Now there are two different methods. We have got method 1. The method 1 is find root 2 by long division method, that is by square root of you know how to find the square root by long division method. So find square root of 2 by long division method, and the decimal expansion what we get is a non-terminating, non-recurring decimal expansion, and therefore it is 100% irrational. Therefore root 2 is an irrational number. This is a direct method or method 1 of proving that root 2 is an irrational number. Now the method number 2, that is second method, is the contradiction method. This is a contradiction method. And what is this method? What is mean by contradiction method? In this method we prove that what is assumed is not true, and so what is not assumed is true. So what is the meaning of this? Let us understand that. Now to show that root 2 is irrational, let us first assume that root 2 is rational. See, please understand here, we have to prove that root 2 is irrational, but we are assuming that root 2 is rational. When I say root 2 is rational, then root 2 is equal to P by Q, because P by Q is a rational number. But P by Q are not co-primes, so convert this P by Q by dividing them by their HCF, we get co-primes, that is A by B, that root 2 is equal to A by B, where A and B are co-primes. Now squaring on both the sides, square root of 2 is square root of 2 square is 2 and a square by b square. Cross product, if you take a square is equal to 2b square, it means that a square here, if you observe carefully, 2 divides a square. See, 2 divides a square because the product means 2 divides a square, and also 2 divides a, that means 2 is a factor of a. Please understand this very carefully. A square is equal to 2b square. It means that 2 divides a square, or 2 divides a, or 2 is a factor of a. That is, let us take it as 2. Now here, in place of if I put it as 2c, because now we know that a is 2 is a factor of a, I can take 2c as any integer 2c which is a, and by placing a as 2c we get 2c square is equal to 2b square, 4c square is equal to 2b square, or 2c square is equal to b square. That means that 2 divides b square, therefore 2 divides b, or 2 is a factor of b. So now we have earlier proved that 2 is a factor of a and 2 is a factor of b also. A and b are co-primes. You see, we had when we assumed we had a and b as co-primes, that means a and b should have a common factor as 1, but we have shown here that a and b has a common factor of 2 also. We have proved that a and b have common factor as 2, which contradicts our assumption that root 2 is rational. So this is a contradiction, okay, and therefore this contradiction has arisen because of our wrong assumption. That means our assumption itself was wrong, what we assumed was wrong, therefore what we have not assumed is that root 2 is irrational, but we assumed it as root 2 as rational, therefore root 2 is irrational here. So this is what is the contradiction method of proving what we call irrational number as irrational. Now show that 5 minus root 3 is irrational. Again, this can be done by contradiction method. Let 5 minus root 3 be rational first. So 5 minus root 3 is a by b, a and b are co-primes here. Now taking a by b to the right and root 3 to the a by b to the left and root 3 to the right, we get 5 minus a by b is equal to root 3. Now simplify this, 5b minus a by b is equal to root 3. Now if you see here, b is an integer, a is an integer, b is an integer again. Therefore in the numerator we have integer and in the denominator we have integer. Therefore integer by integer, that means it is 100% obeys the definition of a rational number. Therefore LHS is a rational number. But on the RHS we have irrational. Now is it possible to have that rational number to be equal to irrational, which is impossible, and this contradiction has arisen because of our wrong assumption that 5 minus root 3 is rational. Therefore our contradiction is corrected by okay, taking that 5 minus root 3 is irrational, and therefore 5 minus root 3 is not rational but irrational. So that therefore we have proved that 5 minus root 3 is irrational. Now coming to the next important discussion as to what is a composite number. A number which has more than two factors is called as a composite number. Please understand this very carefully. 6, if I take 6 as a number, the factors of 6 are 1, 2, 3 and 6. That means 1 divides 6 completely, 2 divides 6 completely, 3 divides 6 completely, 6 also divides 6 completely, and therefore 1, 2, 3 and 6 are factors of 6. And if you see there are 4 factors here, that means this number 6 has more than 2 factors, therefore 6 is a composite number. So please remember that. So any number which has more than 2 factors is a composite number. Now prime number. A number which has only 2 factors is called as a prime number. For example, if I take 5, the factors of 5 are 1 and 5. 1 divides 5, 5 divides 5, and therefore 1 and 5 are the factors of 5. Therefore 5 is a prime number. So please remember that. A number which has only 2 factors is a prime number. Now prime factors of a number. The prime numbers when multiplied give the number are prime factors of the number. What does this mean? Supposing if I write the factors of 6, the factors of 6 are 2 and 3. When I multiply 2 and 3 I get 6, and therefore 2 and 3 are the prime factors of 6. So remember this, the prime factors of a number are the numbers when multiplied we get back the number. That is what they are called as the prime factors. Now prime factorization, the method of expressing a number as a product of prime numbers is known as prime factorization. That means if I have a number 210, I can write it as a product of prime factors 2 raised to 1 into 3 raised to 1 into 5 raised to 1 into 7 raised to 1. That means I have expressed a composite number 210 as a product of only prime factors, and this process of finding the prime factors and expressing it as a product is what is called as prime factorization. So